2015, question 4, answering the following questions about the solubility of calcium hydroxide. KSP is 1.3 times 10 to the negative 6. Write the balanced chemical equation for the dissolution of CaOH2 solid. So basically, CaOH2 solid. When this, remember, this KSP, SP stands for solubility. This is all about things that dissolve product. And the only things that have a KSP value are things that are really, we would call them insoluble, because the definition of insoluble in chemistry is less than 3 grams per liter. So this dissociates into calcium ions and hydroxide ions. I like to use the words calcium hydroxide turns into calcium ions and hydroxide ions, and because of this 2 here, we need a 2 there, and that's the answer for A. B, calculate the molar solubility in 0.1 molar. This is a very difficult problem, but I love it. Here is our equation. And then with KSP, it's the K means it's equilibrium, and you almost always set up a chart for equilibrium. ICE, and this is molarity, and this is molarity, and this is molarity. And then solids do not participate in equilibrium, but I'm going to put negative S here because S stands for solubility. And what happens is some of this goes away as it dissolves. Now, what makes this problem difficult right here is right here. You're not dissolving it in water. You're dissolving it in a calcium nitrate solution. And all nitrates are soluble, and this dissociates into, maybe I should not do that right here. Give me a sec. I'm going to switch colors to like purple. What happens is calcium nitrate, totally not equilibrium, it dissolves into calcium and nitrate. And if this starts out 0.1 molar, in the beginning, at the end, this is 0.1 molar because of the 1-to-1 mole ratio. And then this would be 0.2 molar, but we don't really care about that. But why this problem is interesting is you're used to these being 0, but in this case, this is 0.1. You're not dissolving it in pure water. You're dissolving calcium hydroxide in a solution that also has calcium in it. It's called the common ion effect. This is a 1-to-1 mole ratio, so this goes down S. This is going to go up S. And then because of this 2, this is 2S. And 0 plus 2S is 2S. And S plus 0.1 is S plus 0.1. Remember, S is the solubility, actually the molar solubility. Now, interesting, you're going to look online and they're going to give you, a way to estimate this, but let me just say this. KSP is equal to the concentration of the calcium ion times the concentration of the hydroxide ion squared because of this 2. This is not used because solids and pure liquids do not go into equilibrium. What happens is this is over 1, and it's not a quotient like everything else is. It ends up being just a product because in KSP, the denominator is always 1. Now, this is interesting. You go back to the problem. The problem tells you that this is 1.6 times 10 to the negative 6. The chart tells me that we're going to call this S plus 0.1. And the chart tells me that we're going to call this 2S, but then this has to be squared. An interesting thing happens, they'll go online, they'll go, well, S plus 0.1 is approximately 0.1. The reason why they'll do that is you're going to see when we're all done, S is really, really, really tiny. It comes out to be 0.0018. Well, you can see that 0.1 plus 0.0018 would be 0.1018, 2 decimal places, 4 decimal places. This would need to round to 2. The beauty of the graphing calculator is you don't have to understand, because this is what makes this stuff difficult. You have a solver function on your calculator, and you don't have to understand when you you can make the approximation and when you can't. What happens is, let's just do some advanced algebra. Over here, you have s plus 0.1 times 4s squared. Order of operations, please. Excuse my dear Aunt Sally, exponents. Now I'm going to distribute through, and I end up with 1.6 times 10 to the negative 6 equals 4s cubed, 4s squared times s, plus 0.4, because 0.1 times 4 is 0.4s squared. And so what happens here is, instead of making the approximation, every graphing calculator has a solver function. We're going to put in 4s cubed. By the way, some of you are high-powered ones, and you don't have to have a 0 on one side, and you can just plug this in. But I'm just going to do like the 84. In order to use solver, one side has to be 0. And so this plus this, and then this comes over. And if you put this into solver, S comes out to be 0.0018. And if you go back to your chart, we're looking for the solubility. S stands for solubility. And so molar, and that's the answer. If you do the algebra and you use the approximation, you always also get 0.0018. It's just that there's this 7% rule, and it gets all complicated, and when the solver got introduced, it saved a lot of work. In the box below, complete a particle representation diagram that includes 4 water molecules with proper orientation. All right, and you're supposed to, I always tell you that, probably said this, that water molecules look like Mickey Mouse ears. So here's the deal. Here's what's going on with water. It's one of the most polar compounds. It ends up being an AB2E2, which is bent. Oxygen is the second most electronegative element, so the electrons switch towards the oxygen. So you have 2 polar covalent bonds that are asymmetrically arranged. This side is partially negative. The hydrogen side is partially positive because the electrons shift over to the oxygen. And so what happens is, in these little tiny Mickey Mouse ears, these are the hydrogens, and this is the oxygen. And here's the deal. This is plus. It is going to be attracted to the negative side of the water molecule. So they're going to watch that you drew it like this, that the negative side of the water molecule is what is attracted to the positive ion. You know, now for instance, if they would have given you this problem, they didn't. But I'm just trying to do a little teaching here because I'm really the most concerned about your AP exam. If they were giving you a box like this, and what would have been in here was the nitrate ion, which is -1, then you would have arranged them like this, because the negative ion is attracted to the positive side of the water molecule. So if they would have done something like that, where it was a negative ion, you would have flipped them around. All right, that's a silly question, but I like it. The Lewis electron dot diagram for C2H4 is shown in the box below on the left. In the box on the right, complete the Lewis electron dot diagram for C2H5OH by drawing in all the electron pairs. Here's the deal. Just look at this. I'm going to go over here because we rarely do this in my class. This is why I'm assigning this one. Hydrogen has 2, it wants 2. 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 Carbon has 8. 2, 4, 6, 8. 2, 4, 6, 8. Remember right here, this shared 2 pair is a double bond. You're used to drawing things like this. So here's the deal. Hydrogen has 2, hydrogen has 2, hydrogen has 2, hydrogen has 2. Carbon has 8. This carbon has 8. Now remember, all this line is think of this as a little tiny Venn diagram. A bond means a single bond means a shared pair of electrons. A double bond means 2 shared pair of electrons. I don't like this dot stuff, but you got to go know that it all comes back to this. So the question is, I'm going to switch colors. What do you do? Well, hydrogen has 2, it wants 2. I'm going to circle it and then I'll redo it. This hydrogen needs 2, this hydrogen needs 2, this hydrogen needs 2, this hydrogen needs 2, this hydrogen needs 2. Carbon has 2, 4, 6, 8. So there's 8, 2, 4, 6, 8. Probably should have put the connectings in first. 2, 4, 6, 8. Oxygen has 2 unshared pair. And so now I'm going to quick erase it and just do it again. What maybe I would do is, remember, whenever you kind of have to link the atoms together first. So I'd probably go, this is the linkage between these two, this is the linkage between these two, this is the linkage between these two, this is the linkage between these two. And without drawing the circle, sorry, this is bad. Every carbon has 8, 2, 4, 6, 8, 2, 4, 6, 8. Every hydrogen has 2. This guy has 2, 4, so oxygen has 2 unshared pair not involved in the bonding. You're used to seeing this like this: carbon, carbon, oxygen, hydrogen, boom, 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 and then H, 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 H. But that's what this means, that this region of overlap right here, if I would circle this carbon in red and this carbon in green, this pair of electrons that's in both valence shell at the same time is the single bond. That's what that means. Okay, so then next thing is, what is the approximate carbon, oxygen, hydrogen bond angle in the ethanol molecule? This must be ethanol. This has to be ethanol because it's the only one that has oxygen in it. So basically, this is what you do. If you remember your 9th grade geometry, when you have a big molecule like this, the vertex is really important. So they're interested in carbon, oxygen, hydrogen. So they're interested in this bond angle. Now it looks linear here, but it's not. This is an A, B2, E2. A, the oxygen is hooked to carbon and hydrogen, so 2 different atoms, and then it has 2 unshared pair. And in AB2E2, the parent structure, or the electron domain, they may call it in college, is tetrahedral, because 2 plus 2 is 4. And the tetrahedral angle is 109.5 degrees. And so this is what I would say on this page is slightly less than 109.5 degrees. I don't even know. This is an essay question, so I don't think. Here's the deal. The scoring guidelines said they took any number between 100 and 115. Any number between 100 and 115. They did not take 180, even though it looks like 180 in the picture. Okay, during the dehydration experiment, C2H4 and unreacted C2H5 passed through the tube into water. The C2H4 was quantitatively collected as a gas, but the unreacted C2H5 was not. Explain this observation in terms of intermolecular forces. Okay, they love intermolecular forces. All right, so basically, a lot of times it's not a hard problem because you can't figure out what it's asking. Here's what it's saying. How come when you bubble C2H4 through water, it comes out the other side? But when you try to bubble this gas through water, nothing comes out the other side. And the first thing you got to understand is the reason for that is that ethanol, which is booze, so think scotch, actually dissolves in the water. So the ethanol dissolves in the water. Well, if it dissolves in the water, the gas dissolves in the water, it's not going to bubble out the other side. So the ethanol dissolves in the water. But the C2H4 does not dissolve in the water. And so the question they're really asking you is, C2H4, which they call ethene, does not dissolve in the water. Why? Why? And again, I'm going to say it, like dissolves like dissolves like dissolves like. I'm going to keep saying that. Big letters. Don't put that in your answer, but this, anytime you have a dissolving question, think about my demo with the water and the mineral oil, how it always separates. Like dissolves like means polar liquids dissolve in polar things, dissolve in polar things, nonpolar things dissolve in nonpolar things. And so what this question is getting at is explain this observation in terms of intermolecular forces between water and each of the two gases. So I'm going to extend the page. They want you to talk about each of them. So so let's talk about first C2H4 is non-polar. H2O, polar. And this is a dipole. The water molecules are attracted to each other through dipole-dipole interactions, and in actually a very specific kind of dipole-dipole interaction called hydrogen bonding. Remember, hydrogen bonding is when hydrogen is connected directly to oxygen, nitrogen, or fluorine. And so what happens is, in order for the C2H4 to dissolve in water, it would have to disrupt the hydrogen bonds. This interaction, this C2H4 and H2O is a dipole, induced dipole interaction, which is a weak intermolecular force compared to the dipole-dipole hydrogen bonding force, which is a weak intermolecular force compared to the hydrogen I got to extend this page, which is a weak intermolecular force compared to the hydrogen bonding that occurs in water. So C2H4 does not dissolve in water. Okay, now C2H5OH and water are both dipoles that both exhibit hydrogen bonding. They both have hydrogen bonding. So interesting. What's tricky about this problem is there's hydrogen bonding going between water and water, because remember, hydrogen is connected directly to oxygen. There's hydrogen bonding going on between two molecules of ethanol, because you have oxygen connected directly to hydrogen, and that's why they actually had you draw this molecule so that you could see that hydrogen is connected directly to oxygen. And the weird part is then you have the fact that these are also going to interact, because this is two molecules that both are dipoles that exhibit hydrogen bonding. So is this, and so is this. And because of this interaction, you can disrupt this bond and introduce this bond because they're all roughly the same strength. And so, so because they're both highly polar molecules that exhibit hydrogen bonding, we can say that they always want you to talk about the intermolecular force. The intermolecular force. Now, the reason why I did all this stuff, by the way, is this has to be disrupted and this has to be disrupted. So you put water and ethanol together. This intermolecular force is disrupted. This intermolecular force is disrupted, and they come together. The intermolecular forces between C2H5OH and water are strong enough to disrupt the hydrogen bonding between the water molecules and the ethanol molecules. So the ethanol dissolves in the water. I actually think this is the hardest part of chemistry. So let me just add a little slide here and just show you what I'm talking about. So here's the deal. In the first case, you have this tub with water in it, with all these intermolecular forces between the water molecules that are incredibly strong because of, so this is incredible force. And then you introduce this stuff, which wants to, if it would dissolve in the water, you would need to break this bond and get this intermolecular force to form. This is so much stronger than this that this doesn't happen. But then when you have water in the second case and you introduce C2H5OH, well, this also, and there's this force right here is strong, almost as strong as this. So it is in some cases strong enough to disrupt this. And then you'll get this kind of interaction going on too. And that's what happens when something dissolves.